We are asked to graph this function, the log base 2 with an argument of x minus 3. And in previous videos, I've done this using a standard technique where we first evaluate the intuition of the function. In other words, we want to know where the end behavior is. Now, as long as that base of the log is greater than 1, we could see that the x sign is positive and the y sign is positive. So this end behavior is going to be towards the first quadrant where both the x and y are positive. However, if that base happens to be less than 1, say it's 1/2, the y value switches and it will go to where the x is positive and the y is negative, which is otherwise known as the fourth quadrant. So for this particular graph, we know the end behavior is going to go to the first quadrant, and in terms of the vertical asymptote, we find that by setting the argument equal to 0 and solving for x. Now, in previous videos, the way I've proceeded from here is to set the argument equal to 1, set the argument equal to the base, and set the argument equal to the base raised to the second power. Excuse me. Then we solve for x in each instance, and we get x equals 4, x equals 5, and x equals 2 to the second power plus 3. And we leave it as 2 to the second power for reasons that you'll see in a moment. So at this point, we're going to plug in each of these x values, and when we do that, we see that when we plug in 4, we're going to get 4 minus 3 in the argument. The log base 2 of 1 is 0. We plug in 5. The base of the log matches the base of the argument, so they are going to cancel out, leaving the exponent of the argument. Finally, when we insert 2 to the second power plus 3 into our argument, we could see the plus 3 and minus 3 cancel out. Here, now, in the argument, we have 2 to the second power. Everything cancels out except for the exponent, and we end up with a y value of 2. Excuse me. Now, if you want to get an additional point, you could set it 2 to the third power. But for now, here we go. When we simplify everything, we get the following xy coordinates. When we use our vertical asymptote and head towards the first quadrant as predicted, this is our resultant graph. Now let's go to Desmos and check this out. We went ahead and plotted our vertical asymptote at x equals 3. We then plotted each of the points, and you could see that this graph matches the first line, which is Desmos' graph. Now folks, in this video, we're going to do things a little bit differently. Here, we will endeavor to graph the parent function. So we're going to change this to y equals log base 2 to the x. And we're going to set up a table where we're actually going to pick y values over a broad spectrum of the xy plane. We're going to start at -2, then we're going to go to -1, 0, 1, and 2. Now going back to the parent function, if we perform what I call whirlybird, and we take the base, we raise it to the opposite sign of the equal sign, we get 2 to the y, and that is going to equal our x value. So in this particular technique, we're going to pick our y values, we're going to input the y values, and we're going to use whirlybird to get the x values. And here you could see that 2 to the -2 power will yield an x value of 1 over 2 squared, which is 1/4, 2 to the -1, 1/2, 2 to the 0, 1, 2 to the first power is 2, and 2 squared is 4. Now remember folks, this is not our final graph. Our final graph is a transformation of this parent function. So next, what we're going to do is examine the transformation and recognize that this is a horizontal translation, and because there's a -3, we're actually having a horizontal transformation to the right of 3. Remember, the inside of the function lies. So here, even though it says x minus 3, we're going to end up adding 3 to all the x values. Now we're going to keep the y values as is, and we're going to add 3 to each of the x values, keeping the y values as is, and this is going to result in the following table. Next, we are going to plot our points. And when we plot our points on Desmos, we will see that it creates a graph very similar to the red graph created by Desmos. Next, we are asked to graph this logarithmic function, and we're going to use the technique that I described most recently. Namely, we're going to go ahead and find a table of values for the parent function. In this case, that's going to be log base 2 of x, and then we're going to apply the transformations. So let's change this to y equals log base 2 of x, and if we apply what I call whirlybird, we're going to find that 2 to the y will equal x. So as in the most recent example, we're going to actually choose an array of y values that span over the negative portion of the graph as well as the positive portion of the graph. And then we're going to use this equation to find our respective x values. So first, let's just do the first one. When y equals -2, we plug in -2 for y, and that gives us our x value. So we're going to have 2 to the -2 is the same as 1 over 2 squared, right? We flip that fraction, we flip the fraction, then we change the sign of the exponent. And that's going to give us 1 over 4. When we have -1, we're going to have 2 to the -1, which is going to equal 1/2. 2 to the 0 is going to equal 1. 2 to the first power is going to equal 2. And finally, 2 to the second power is going to equal 4. Now, folks, the game plan is to apply these transformations. So let's look at the x values first. Whenever the parentheses appears like this, namely, there is not a GCF pulled out, we could very easily pull out a GCF of 2. But when there's no GCF, this positive 4 goes first and then the 2. So in this case, we are going to do the opposite of what this says. So this is a positive 4, therefore the first thing we're going to do is a translation to the left, or do x minus 4. Then, second, we're going to do what that 2 tells us to do, that's the b value, and we divide by the b value. So dividing by 2 will then give us our final x value. Or you could think of it as this. You do x minus 4, and then instead of dividing by 2, we're going to multiply by 1/2. Either way. With respect to the y values, it's much simpler. We're going to take this vertical stretch and multiply it by the y value, and then we're going to do a shift vertically plus 1. So let's go back, let's apply these transformations, and then come back and see what our new table looks like. Let's now take the values from the parent function and apply the transformations. Okay, starting with x equals 1/4, we're going to have 1 over 4 minus 4 in the numerator, and 4 is the same as 16 over 4. That's going to equal 15 over 4. We're going to divide that by 2, and we're going to end up with negative 15 over 8. Now, with respect to the y value, we're going to take our y value, which is negative 2, we're going to multiply it by 3, and then we're going to add 1. So we're going to have negative 6 plus 1 is going to be negative 5. Next, with the x value of 1/2 in the numerator, we're going to have 1/2 minus 4, and 4 is going to be 8 over 2. That's going to be negative 7 over 2. We're then going to divide by 2, and we're going to end up with an x value of negative 7 over 4. In terms of our y value, much easier. Here's our negative 1. We're going to do 3 times negative 1 plus 1. We're going to get negative 3 plus 1, otherwise known as negative 2. Okay, these are our y values so far. These are our x values so far. Okay, it gets a little bit easier when we don't have fractions. We're going to have in the numerator 1 minus 4, which is negative 3. Then we're going to divide by 2, and we're going to have negative 3 over 2. And in terms of our y value, we're going to have 3 times 1, which is 3. 3, I'm sorry, we're going to have 3 times 0, which is 0, plus 1, and that gives us a y value of 1. Okay, folks, let's clean this up a little bit and then proceed. So we have these are x values, and these are our y values. Okay. So far. Okay, now let's keep going. Our next x value is going to be x equals 2 that we're plugging in. When we plug in 2 on the top, we have 2 minus 4 is negative 2. Divided by 1/2 will give us negative 1. When we take a y value of 1 and multiply it by 3 and add 1, we're going to get a 4. Next, we're going to take an x value of 4. 4 minus 4 is 0 over 2, which is 0. And we're going to take a y value of 2, plug it in. 3 times 2 is 6, plus 1 is 7. Now, folks, we have our x and y coordinates of the new transformed function. Okay, and in anticipation of graphing this function, we're going to change these fractions to decimals. We've done that. Here's our x and y coordinates. Okay, folks, I went ahead and went to Desmos. And first, to check our math, I wrote this as f of x equals our original function, and then I did f of negative 1.875, and you can see here the calculator gives us negative 5. F of negative 1.75, we get negative 2. And we can see that reflects our original table. F of negative 1.875 is indeed negative 5. F of negative 1.75 is indeed negative 2. And I went ahead and did that with all of our x values, and I confirmed the y values. Then I went ahead and plugged these, I graphed each of these points individually. I got these points on the graph, and you could see our original graph right here, f of x equals 3 log base 2 with an argument of 2x plus 4 plus 1 fits the points on our graph. Folks, before we leave this example, I want to point out that I forgot to discuss the vertical asymptote and the end behavior. First, for the end behavior, because there's a positive out here and a positive in front of the x, and that base is greater than 1, we know that our end behavior is heading towards the first quadrant. And in terms of finding the vertical asymptote, we're going to take the argument and set it equal to 0. We're going to get 2x equals negative 4 and x equals negative 2. And I went ahead and graphed that like so. See our vertical asymptote in our graph heading towards the first quadrant. We are given this exponential equation, and I'm going to review a technique that I've shown in previous videos, and then we're going to use a new technique where we're going to graph the parent function and we're going to apply the transformations. So the way I've talked about doing this previously is first to discuss the intuition. So this is a growth function, and here's your horizontal asymptote. So the first thing to do is graph the horizontal asymptote at y equals positive 1, and because this is a positive out in front, you know that the graph is going to start above the horizontal asymptote, and as you move left to right, it's going to go away from the horizontal asymptote. So this is the rough intuition of the graph. Now the way I like to graph these is to go ahead and have that intuition in mind, have the horizontal asymptote set up, and then do the following. I take whatever this complex is up here in the exponent, and I set it equal to 0, and I set it equal to 1. Then I go ahead and I solve for x. So here we're going to have, I'm sorry, this is not correct. We're going to have x plus 2 set equal to 0 and x plus 2 equal 1. That's going to yield a value of x equals 2 and x equals negative 1. Then, folks, we're going to go ahead and set up a table. We're going to put our newfound x values here, and then we're going to do f of each of these values to get our y value. Okay, so we're simply going to take these x values and plug it into our function. First, we're going to have 3 times 2 to the negative 2 plus 2 plus 1. That's going to be 3 times 2 to the 0 plus 1. Anything to the 0 power is 1. Therefore, we're going to have 3 times 1 is 3 plus 1 is 4. Next, we're going to plug in negative 1. We're going to have 3 times 2 raised to the negative 1 plus 2 plus 1. 3 times 2 to the first power plus 1. And 2 to the first power is 2. 3 times 2 is 6. Plus 1 is 7. You see, folks, this is designed on purpose because when you set this equal to 0, set that equal to 1, get your x value, and then you end up plugging it into the complex, you end up getting 0 and 1 back, and the math is very easy. So now we have our points, and we're simply going to plot these, and in combination with the intuition, we're going to have a reasonably accurate graph. So here we're going to have negative 2 comma 4 is going to be somewhere here, and negative 1 comma 7 is going to be like so, and you're going to get a graph that moves up as you move away from the horizontal asymptote, moving left to right. And if we go ahead and graph this on Desmos, here's our original function, here's our horizontal asymptote. I went ahead and set up our chart, negative 2 comma 4, negative 1 comma 7, I did f of these x values to confirm that our math was correct, that we got 4 and 7 respectively for the y values. Then I went ahead and plotted these points, negative 2 comma 4, negative 1 comma 7, and you could see the red line, curved line, is our graph as per Desmos, and all of the points, both of the points I should say, are on the line. We're going to use a technique featured in this video, whereby we graph the parent function and we apply the transformations. So the parent function for this exponential function would be just y equals 2 to the x. This time, folks, we're going to choose our x values over an array spanning from negative 2 all the way to positive 2 with 0 in the middle. We're then simply going to plug in negative 2 into this parent function. We're going to get 2 to the negative 2. We're going to flip that fraction. That's 1 over 2 squared, otherwise known as 1/4. Here we're going to get 1 over 2. Continuing, we're plugging in 0 into that parent function. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. Now, folks, we're going to apply this transformation. Here, in terms of the x, we could see we have x plus 2. The inside lies. That means this is going to be a shift to the left 2. We're going to take all our x values and subtract 2. In terms of the y, always simpler. We have a vertical stretch of 3 and a vertical translation of 1 unit up. So we're going to take our y value here in the table that corresponds with its x value, multiply it by 3, and add 1. So here we go. Here's our x values. You could see we took -2, we subtracted 2, we got -4. -1 minus 2 is -3. 0 minus 2 is -2, and so on. With respect to the y values, we first multiplied by 3. 3 times 1/4 is 3/4. Then we added 1. 3 times 1/2 is 3/2. Then we added 1. 3 times 1 is 3, plus 1 is 4. 3 times 2 is 6, plus 1 is 7. And finally, 3 times 4 is 12, plus 1 is 13. I went ahead and changed the fractions to decimals, which makes it easier to graph. Folks, I then took these points, -4, 1.75, -3, 2.5, -2, 4. I went ahead and graphed these on Desmos, and you could see here's all our points, -4, 1.75, -3, 2.5, and so on. This red line here is the Desmos graph, and you could see all of our points are on the graph.